Lecture 9, Token based distributed mutual exclusion algorithms. Preface, recap of previous lecture. In previous lecture we have discussed about quorum based approaches, that is given by Mikawa's algorithm and Agarwal al-Abadi quorum based algorithms for distributed mutual exclusion. Content of this lecture. In this lecture we will discuss about the token based approaches, namely Suzuki-Kasami's broadcast algorithm and Raymond's tree based algorithms. So, token based algorithms uses a unique token, and this unique token is shared among the sites. Sites holding the token can allow to go into a critical section repeatedly until it sends this token to some other sites. Numerous token based algorithms are available and they differ in the method how the sites carries out the search for the token in the network. So, token based algorithms use sequence numbers instead of time stamps. Sequence number distinguishes between old and current requests. The proof of correctness in token based algorithm is trivial, but the issues which are challenging in design of token based algorithms for distributed mutual exclusions are the freedom from starvation, freedom from deadlock, and the detection of token loss and the regeneration of the lost token. Token based approaches. So, token based algorithms, a unique token is shared among the sites and site is allowed to enter into critical section if it possesses the token. Token based algorithms use sequence numbers instead of time stamps. This sequence number used to distinguish between an old and the current requests for the token. The correctness proof of token based algorithm that they enforce mutual exclusion is trivial because the algorithm guarantees mutual exclusion so long as the site holds the token during the execution of the critical section. In this lecture we will discuss about two token based approaches, namely Suzuki-Kasami's broadcast algorithm and Raymond's tree based algorithms. Suzuki-Kasami's broadcast algorithm. In Suzuki-Kasami's broadcast algorithm, here if a site wants to enter into a critical section, it does not have the token, then it broadcasts a request message for the token to all other sites. So, a site which possesses the token sends it to the requesting sites upon the receipt of the request message. If the site receives a request message when it is executing the critical section, it sends the token only after it has completed the execution of the critical section. This algorithm efficiently addresses the following two design issues: how to distinguish an outdated request message from a current request message. As I told you, it uses the sequence numbers to basically answer this particular question. The second issue here is how to determine which site has an outstanding request for the critical section. So, after a site finished the execution of a critical section, it must determine what sites have an outstanding request for the critical section, so that token can be dispatched to them. And to do this, the algorithm uses different data structure and variables that we are going to describe now in details. So, the first issue, that means how to distinguish an outdated request message from the current request message, is addressed in the following manner. So, a request message of a site Sj has the form request j comma n, where n is the sequence numbers which indicates that site Sj is requesting its nth CS or a critical section execution. So, a site Si keeps an array of integer called RNI 1 to n, where RNI of j denotes the largest sequence number received in the request message so far from site as j. So, all the sites keeps this particular variable, that is Rn of all the sites. When a site Si receives a request j comma n from process j, it sets its request number variables Rni of j is equal to the maximum of Rni of j comma n. So, when a site Si receives the request j comma n message, the request is outdated if Rn of I of j is greater than n. So, this condition, that means if Rn I of j denotes the denotes the critical section earlier request, and if the current request, that is Sn, is basically less than or a previous, or it's an, then it will be designated as an old request. For critical section. So, this particular inequality will ensure that, or will basically keep check that request is whether current one or it's an outdated, and it uses the sequence number n. Of the requesting message. The second issue is addressed in the following manner. So, the second, let me remind you, second issue says that how to determine whether the site has an outstanding request for the critical section. So, this is called a second issue. That means when a particular critical section is idle, or a process or a site exits the critical section, then it has to know which of the sites are basically having the pending requests, and this is called second issue, and it is addressed in the following manner. So, the token consists of queue of requesting sites, that is capital Q, and an array of integers ln 1 to n, where ln j is the sequence number of the request which site Sj has executed most recently. So, after executing its critical section, a site Si updates ln I as Rni of I to indicate that its request corresponding to the sequence number Rn of I has been executed. Now, at a site Si, if Rni of j is equal to ln j plus 1, this inequality, then site Sj is currently requesting the token. So, to summarize these 2 points, so first thing is the token is nothing but it consists of a queue of requesting sites. Plus it also contains an array of integers, that is called ln I is the sequence numbers of the request which site Sj executed most recently. So, array of requests executed, that is indicated by ln. So, these two information is basically makes this particular token. So, when if Rn, that is the request coming from j, if it is equal to ln of j plus 1, then it has a pending, then the site is currently requesting for a token. So, this will be the indication that a site, that these are the set of sites which are basically having a pending request for the token. So there comes the algorithm. Algorithm has these different steps. The first step of this algorithm is about requesting for a critical section. So requesting the critical section, first step says that if requesting site Si does not have the token, then it increments its sequence number, that is Rn I of I, and sends the request I comma Sn, that is a sequence number, message to all other sites. So Sn is updated value of Rn I of I. Now when a site Sj receives this particular message, it sets Rn of j's I to the maximum of Rn j of I and Sn. Now if Sn has the idle token, then it sends the token to Si if Rn of j of I is equal to ln of I plus 1, that is, it is having the pending request for the token. Now the next step of the algorithm is executing the critical section. Si executes the critical section after it has received the token. Third step is about releasing the critical section. Having finished the execution of critical section, the site Si takes the following actions. It sets ln I element of the token array equal to Rni for every site Sj whose ID is not in the token queue. It appends its ID in the token queue if Rn of I of j is equal to ln of j plus 1. If the token queue is non-empty after the above update, Si deletes the top site ID from the token queue and sends the token to the site indicated by the ID. So this we can see through this illustrative example. So initially there are 5 sites and they are now requesting. So Rn of j denotes the sequence number of the latest request from a process j, and ln j denotes the sequence number of the latest visit to the critical section for a process j. So just see that. So site 1 over here, site 0 here is requesting for the critical section entry. So it is modifying. When the message is flowing to basically 1 and 2, so 1 and 2 has received this particular request and the queue will be updated as 1 and 2. They are having the pending request. So in this way the algorithm proceeds and the token is finally being delivered. Now the correctness of this algorithm. Mutual exclusion is guaranteed because there is only one token in the system and the site holds the token during the critical section execution. Theorem: a requesting site enters the critical section in a finite time. Proof: the token request message of a site Si reach the other site in a finite amount of time. Since one of these sites will have token in a finite time, site Si's request will be placed in the token queue in a finite amount of time. Since there can be at most n-1 request in front of this request in the token queue, so site Si will get the token eventually and execute the critical section in a finite amount of time. Performance: no message is needed and the synchronization delay is 0 if the site holds the idle token at the time of its request. So if a site does not hold the token when it makes a request, the algorithm requires n messages to obtain the token. Hence the synchronization delay is idle in the first case, or the synchronization delay is at most t. where n number of messages are required. Raymond's tree based algorithm. This algorithm uses a spanning tree of the network to reduce the number of messages exchanged per critical section execution. Hence, this is an optimized algorithm as far as number of messages are concerned, but it uses a structure that is basically the spanning tree. So, it assumes that the spanning tree of the network is available. Now, the network is viewed as a graph, that is a spanning tree of the network is a tree that contains all n nodes. So, the algorithm assumes that the underlying network guarantees the message delivery. So, that means it is a reliable communication channel, it assumes. So, all the nodes of the network are completely reliable. So, there is no assumption of the failures, it is assumed that the nodes are reliable. The algorithm operates on a minimum spanning tree. So, the spanning tree is basically the minimum spanning tree which is required in the algorithm of the topology. The algorithm assumes the network node to be arranged in an unrooted tree structure. The next figure shows the spanning tree of 7 nodes and the message between the node traverse along the undirected edges of the tree. A node needs to hold the information about and communicate only to its immediate neighbors. Similar to the concept of token used in token based algorithm, this algorithm uses the concept of privilege. Only one node can be in a position of the privilege called the privileged node at any time, except when the privilege is in transit from one node to another node in the form of the privilege message. So, at any time, at any point of time, at most one node holds the privilege and called the privileged node. So, when there are no nodes requesting for the privilege, it remains in the position of the node that last used it. Now, the variables which are used here in Raymond's algorithm are as follows. So, the first variable is called the holder variable. Now, holder variable will impose a directed tree over an undirected graph or an undirected tree which we have seen. So, each node maintains a holder variable that provides the information about the placement of privilege in relation to the node itself. A node stores in its holder variable the identity of the node that it thinks has the privilege or leads to the node having the privilege. So, for two nodes x and y, if holder of x is equal to y, then we could redraw an undirected edge between x and y as the directed edge. So, holder variable will impose or will basically impose the directed structure on top of that. So, for instance, if a node G holds the privilege, in the next figure we will show, and the figure can be redrawn with logically directed edges as shown in figure 9.3. So, here we can see that the previous figure which shows you the undirected graph. So, using holder variable, this will basically induce a directed structure of a tree, and this basically directions are pointing towards the node which is currently holding the token. So, if C is a node which is a neighbor of a node which is holding the privileged token, will have an edge, and D can direct its edge towards the node who in turn knows the privileged node. So, that way all the nodes will basically place, as far as G is concerned, which is holding the token or a privileged node, will basically put self in holder of G. So, holder of G is nothing but the self, and the holder of D is nothing but C. Holder of C is nothing but G. Holder of B is nothing but C. Holder of F is nothing but B. Holder of E is nothing but A, and holder of A is nothing but B. So these particular holder variables will induce a directed structure on an undirected spanning tree. Now suppose node B that does not hold the privilege wants to execute the critical section. So B sends the request message to the holder of B, that is C, which in turn forwards the request message to the holder C, that is G. The privilege node G, if no longer needs the privilege, sends the privilege message to its neighbor which made a request for the privilege on behalf of B and resets the holder variable holder of G is equal to C. Node C in turn forwards the privilege to node B since it has requested the privilege on behalf of B. Node C also resets. So basically the tree will look like in this particular manner. Now here the node C forwards the privilege message on behalf of G to the requested node, that is B, and node G no longer needs the privilege, so it sends the privilege to C and will change its holder variable. Holder of G will become now C and holder of C will become as B. So these arrows will be changed in this manner and this will now contain the privilege node. So I have explained, and the same thing is basically illustrated in this particular example. Now another example shows that the node which is currently holding the token is basically the token holder, that is the root, that is S1. Now side S5 sends a token request. So it will send first to S2 and S2 on behalf of S5 will send a token request to S1. So S1, if it is not using the privilege at that point of time, then it will, and basically that request from S2 is at the top of its request queue, then it will send the token to S2. So holder of S1 is also need to be changed to S2. Now S2 will send the token to S5 and the holder of S2 is also changed to S5 and S5 becomes the new token holder. So the data structures used in Raymond's algorithms, at each node the following variables are used which are summarized as follows. Variable name holder. Holder will contain either the self if the token or the privilege is with the node itself, or the identity of one of the immediate neighbors. Using variable is true or false. So using variable indicates if the current node is executing the critical section. So if the node currently executing into the critical section, its using variable will be flagged as true. Request queue is a FIFO queue that contains self or the identities of the immediate neighbors as the elements. Request queue of a node consists of the identities of those immediate neighbors that have requested for privilege but have not been sent the privilege. Asked is true or false indicates if the node has sent a request for the privilege. So the data structures, the value self is placed in the request queue if the node makes a request for the privilege for its own use. The maximum size of the request queue of a node is the number of immediate neighbors plus 1 for self. Asked prevents the sending of duplicate requests for the privilege and also makes sure that the request queue of the various nodes do not contain any duplicate elements. So the algorithm consists of the following routines. So first routine is assign privilege, make request. Assign privilege. This routine sends a privilege message. A privileged node sends a privilege message if it holds the privilege but is not using it. Its request queue is not empty and the elements at the head of its request queue is not the self. Assign privilege. A situation where self is at the head of the request queue may occur immediately after the node receives a privilege message. So the node will enter into the critical section after removing self from the head of the request queue. If the ID of another node is at the head of request queue, then it is removed from the queue and a privilege message is sent to that node. Also, the variable asked is set to false since the currently privileged node will not have sent a request for the privilege message. Make request. This is a routine which sends the request message. An unprivileged node sends a request message if it does not hold the privilege, its request queue is not empty, that is, requires the privilege for itself or on behalf of one of its immediate neighbor nodes, and it has not sent the request message already. Make request. The variable asked is set to true to reflect the sending of the request message. The make request routine makes no change to any other variable. The variable asked will be true at the node when it has sent the request message to an immediate neighbor and has not received a response. A node does not send any request message if asked is true at that node. Thus, the variable asked makes sure that unnecessary request messages are not sent from the unprivileged node. This makes a request queue of any node bounded even when operating under heavy load. Below we mentioned 4 events that constitutes the algorithm. So the first event says that a node wishes to execute the critical section. So this particular aspect basically is handled by the algorithmic functionality such as enqueue, request queue, and self, assign privilege, and make request. A node receives a request message from one of its immediate neighbors X, enqueue, request queue, and X. A node receives a privilege message, then in that case holder will become to self and assign the privilege and make request. A node exits the critical section, using will become false and assign privilege and make request. Events. A node wishes the critical section entry. If it is the privileged node and the node could enter the critical section using assign privilege routine, otherwise it sends the request message using make request routine. A node receives a request from one of its immediate neighbor. If the node is the current holder, it may send the privilege to the requesting node using the assign privilege routine, otherwise it forwards the request using make request routine. A node receives the privilege message. The assign privilege routine could result in the execution of the critical section at the node, or it may forward the privilege to another node. After the privilege is forwarded, the make request routine could send a request message to recover the privilege for the pending request at this node. A node exits the critical section. On exit the critical section, this node may pass the privilege on to a requesting node using assign privilege routine. It may then use the make request routine to get back the privilege for pending request. So this particular picture will represent or illustrates the message overtaking. This algorithm does away with the use of sequence numbers. The algorithm works such that the message flow between any two neighboring nodes sticks to a logical pattern. So if at all the message overtaking occurs between node A and B, it can occur when privilege message is sent from node A to node B, which is then very closely followed by the request message from node to such a message overtaking will not affect the operation of the algorithm. You can see through this particular example. So if node A and B So if node A is sending the it can node A is sent to node B 2 requests, and such that the previously sent request is basically arriving late, and so basically here this so it has sent the privilege, and then immediately A wants that privilege to be used, so it will send the request. So at the side B, the request will arrive first, although it is not having the privilege, so it will be put in the queue of request queue of B. So once the privilege arrives at B, so B will become a privileged node. So it becomes a privileged node, then basically it will check the request queue, and the A will be on the head of the queue. It will dequeue it, and it will send the reply, it will send the privilege back again to A. So even this kind of example where this is called a message overtaking is not going to affect the working of this algorithm. So when a node B receives the privilege message from A, after receiving the request message, it could enter the critical section, or it could send the privilege message to an immediate neighbor at the head of the request queue, which need not be node A. So the message overtaking does not affect the algorithm that I have explained. Now correctness. The algorithm provides the following guarantees. Mutual exclusion is guaranteed, then deadlock is impossible, starvation is impossible. Mutual exclusion ensures that at any instant of time, not more than one node holds the privilege message, hence the mutual exclusion is guaranteed. So whenever a node receives a privilege message, it becomes privileged. Similarly, whenever a node sends a privilege message, it becomes unprivileged. Between the instants, one node becomes unprivileged and another node becomes privileged. There is no privileged node. Thus, there is at most one privileged node at any point of time in the network. Deadlock is impossible. So when the critical section is free, one or more nodes want to enter the critical section but are not able to do so, a deadlock may occur. This could happen due to one of the following scenarios. A privilege cannot be transferred to a node because no node holds the privilege. A node is in possession of privilege is unaware that there is other nodes requiring the privilege. The privilege message does not reach the requesting unprivileged node. So all three conditions, which basically possibly will lead to a deadlock, is not possible here in the algorithm, or is taken care by the algorithm. Hence there is deadlock is impossible. So these are basically the scenarios in which none of these three conditions will arise, which will basically the region to become the deadlock in the algorithm. So scenario 1 says that scenario 1 can never occur in this algorithm because nodes do not fail and the message are not lost. This is the assumption of the algorithm. The logical pattern established using the holder variable ensures that the node that needs the privilege sends a request message either to the node holding the privilege or to the node that has a path which leads to the token. Thus scenario 2 also cannot happen. That is, node in the position of the privilege is unaware that there are other nodes requiring the privilege. The series of request messages are enqueued in the request queue of various nodes, such as request queues of those nodes collectively provide the logical path for the transfer of privilege message from the privileged node to the requesting unprivileged node. So scenario 3 can never occur. Hence the starvation is impossible in this algorithm. Third, another aspect is called starvation. Starvation is also impossible. When a node A holds the privilege and another node B requests for the privilege, the identity of node B or the IDs of the proxy nodes of node B will be present in the request queues of various nodes in the path connecting the requesting node to the currently privileged node. So depending upon the position of ID of the node B in those request queues, node B will sooner or later receive the privilege. Thus once the node B's request message reaches the privileged node A, node B is sure to receive the privilege. So hence the starvation is also impossible. Now, cost and performance analysis of the algorithm. In the worst case, the algorithm requires 2 times longest path length of the tree, that number of messages per critical section entry. This happens when the privilege is to be passed between the nodes at the either end of the longest path of a minimum spanning tree. The worst possible network topology of this algorithm is where all the nodes are arranged in a linear fashion and the longest path will be n-1, and thus the algorithm will exchange 2 times n-1 message per critical section. However, if all the nodes generate equal number of request messages for the privilege, the average number of messages needed per critical section entry will approximately be 2 times n/3, because the average distance between a requesting node and a privileged node is n+1/3. The best topology for the algorithm is the radiating star topology. The worst case cost of this algorithm for this topology is of the order log to the base k-1 n. So trees with higher fan-outs are preferred over radiating star topologies. The longest path length of such trees is typically of the order log n. Thus, on an average, this algorithm involves the exchange of order log n messages per critical section execution. Under the heavy load, the algorithm exhibits an interesting property. As the number of nodes requesting the privileges increases, the number of message exchange per critical section entry decreases. Hence, in the heavy load, the algorithm requires a message exchange of only 4 messages per critical section entry. Now, this particular comparison of different distributed mutual exclusion algorithm, we have seen the approaches which are called Lamport and Rickert-Agarwala algorithm. They are non-token based algorithms, and here the synchronization delay was t, and the messages required in Lamport was 3 times n-1. Rickert-Agarwala was basically able to complete this in 2 n-1. Now, in Lamport's algorithm, basically the priority or the fairness is achieved through the timestamps, and Rickert-Agarwala algorithm uses implicit release message strategy. Now, the another class of algorithm which we have seen is based on quorum based algorithms. Here the number of messages are to be reduced. Why? Because the permissions are not taken from everyone, but from a quorum or a subset of the sets. There are 2 algorithms we have seen, Mikawa's algorithm and Agarwal-Al-Abadi algorithm. Both algorithms, they take response time 2 times t, but the messages were quite reduced here in this case. So, messages in the low load 3 times root n, and in Agarwala algorithm log n. Now, another class of algorithm we have seen for mutual exclusion is called token based algorithms. In token based algorithm, today we have seen 2 different algorithms, Suzuki-Kasami and Raymond tree algorithm. These algorithms require the synchronization delay st and this t times log n/2 different messages. Now, Suzuki-Kasami algorithm and Raymond tree algorithm are based on the token. So, the node which is holding a token basically will be, so that means there is only single token. So, mutual exclusion guarantee is trivial, but all other aspects we have seen for the working of the algorithm, that there should be deadlock free, starvation free, and the token loss is to be taken care of, and regeneration of token also is to be taken care of. So, and how the token are to be searched depends upon, in Raymond tree, that is in the tree structure, finding token is quite easy. As far as Suzuki-Kasami algorithm, it's a broadcast algorithm, so the messages are sent to all. So, all these algorithms are there, it depends upon different applications, in which application which algorithm is going to be useful. So, based on these parameters or performance parameters, these algorithms are selected and used for different applications. Now, conclusion. Mutual exclusion is a fundamental problem in distributed computing system where concurrent access to the shared resource or a data is serialized. In distributed mutual exclusion algorithm, we have discussed 3 types of algorithms: non-token based, quorum based, and token based approach. In upcoming lectures, we will discuss about consensus and agreement algorithms. Thank you.